Okay. So the advantage here is that really to do this variation of parameters method, I need these 5 formulas. So if I want to solve here, solve a differential equation that I couldn't do using the previous method. So here's what I consider to be a relatively straightforward example. I can't do this by undetermined coefficients. And the reason I can't is because secant is not one of the acceptable trig formulas to use undetermined coefficients on. I can only do it with cosines and sines. Well, F you. Okay, fine, I got to do it this way. So the first thing I need is y1 and y2. Those are the solutions to the homogeneous equation. So let's go through that first. So from here, what does this give me as my homogeneous solution? Okay, because it's r squared plus 1 equals 0, so r equals plus or minus I. So the two equations, yc is c1 y1 plus c2 y2. What are y1 and y2? Exactly. Okay. Y1, y2, f of x. So I need the Wronskian for y1 and y2. I'm using the formulas that were at the top of the screen right here. And then I take the determinant, AD minus BC, and I get but that bottom left is already a minus sign, which makes this cosine squared plus sine squared. Yay! Now I need two other determinants for W1, I'm going to replace the first column with a 0 at the top and my f of x at the bottom. For W2, I'm going to replace the second column. And again, I want you to tell me what these determinants are. Right, because I'm going to get 0 minus sine times secant, but secant's 1 over cosine. That's sine over cosine, that's tangent. What about the second one? Careful. The sine x is multiplied by 0. So that goes away, and I just get cosine times secant, which is 1. Hey, wait a minute. According to the formula up here, U1 prime is W1 over W. And U2 prime is W2 over W, but W is just 1. So I get U1 prime is negative tangent of x over 1. U2 prime is 1 over 1. I know how to integrate. What's the integral of 1? Good. So U2, integral of 1 dx is just x. You might think, wait a minute, don't I need a plus c? I promise we don't, and I'll explain why in a minute. But over here to do U1, I need to do the integral of negative tangent. Put the parentheses facing the wrong direction. Let's get rid of that parenthesis. How do I integrate tangent again? Seeing you were worried about forgetting all those Calc 1 integral tricks. That's the integral of minus sine of x over cosine x dx. If I do the u sub for cosine of x, then the derivative of cosine is minus sine. So this is 1 over u. What's the integral of 1 over u? So I get ln cosine of x. Again, I really don't need a plus c. All right. I have U1 and U2. Based on what we said on Friday, what the hell do I do with them? All of what we have done here is to replace what we were doing with undetermined coefficients, which was finding the particular solution yp. And the particular solution used u1, u2 instead of c1 and c2. Our parameters in the complementary solution now vary and they become these functions. So yp is u1, y1, u2, y2. In our case, that's ln of cosine of x times what? What was y1 again? Cosine of x. And then plus x times sine of x. Which means our general solution is c1 cosine x plus c2 sine x plus ln x. Oh, sorry, no, not ln of x. ln cosine of x times cosine of x plus x sine of x. Got to write down the right, Josh. Hey, once I have the formula in front of me, this is pretty damn fast. Questions? I'm sorry? I got one though. Why don't I need the plus c? I did two integrals up here. Why didn't I need a plus c? And if I added a plus c to that x, then I would have multiplied it by sine x, right? And that would have been c sine x. And that's already right here. It's exactly the reason. The plus c's in those two integrals for u1 and u2 are already in these plus c's. I don't need them. Whew. Now, in this case, my complementary equation, the complementary solution to the corresponding homogeneous equation, had cosine and sine because we ended up with complex numbers. This method literally doesn't care what you use. Oh, hang on a second. An interesting note. Back up here, when I started this problem, I had secant of x. Secant of x is 1 over cosine of x, right? That means cosine can't be 0. In my integrals, I end up with an ln of cosine of x, which means the cosine of x can't be 0. My interval popped right back. Same idea here. When I set this problem up, this is what they give me. Solve this non-homogeneous equation. Okay. Absolutely 1 over 1 plus e to the x is screwing with me. And e to the x, e to the number x, I could deal with that. But 1 over? No, as soon as I introduce rational functions, undetermined coefficients goes right out the window. I have to do this by variation of parameters. So what do you do? What do I do first? Start with the homogeneous version, set it equal to 0, solve that. I need my auxiliary equation, and I need the roots of it to get the corresponding homogeneous solution. So my roots are -2 and -1. So I get the complementary solution is C1 e to the -2x plus C2 e to the -x. I don't care which order you put those in, it doesn't matter to me. If you wrote it R plus 1, R plus 2, you'll have them in the other order. Big deal. So I now need 3 determinants. The Wronskian of these two, the Wronskian with one column replaced, and then the Wronskian with the other column replaced. What goes on my second line? So when I do that and multiply here, I get minus e to the -3x, because when you multiply with the same base, you add the powers, minus, -2, so that becomes plus e to the -3x. Well, -1 plus 2 is +1, e to the -3x. Now, I replace the first column for W1 with a 0 on top and my solution on the bottom. So when I do the first two, that's a 0 minus e to the -x over 1 plus e to the x. When I do W2, I replace the other column. And this time, this multiplication is 0, so I just get this. E to the -2x over 1 plus e to the x. So far, so good? Here's the disgusting part. U1 prime is W1 over W. So that's minus e to the -x over 1 plus e to the x times 1 over e to the -3x. I wrote it as W1 times 1 over W. Ew. All right. Let's resolve those. I get minus e to the 2x over 1 plus e to the x. I'm going to need to integrate this. What do I do with this? See, this is where the problems start to show up. I did all the formulaic work, now I gotta go back and do integrals again. Calc 1. I promise this is just Calc 1 integral. It's just a little messy, Calc 1 integral. All I'm gonna do is a sub. I got too many U's. I'm gonna use a different letter. How about a V? Let's write V equals e to the x. Then what's dV? There's more. Okay, wait a second. That means I need an e to the x here. What if we take e to the, oh, see, I made a copy error. That should be e to the 2x. What if we take one of those, e to the 2x is e to the x times e to the x. You multiply with the same base, you add them. So let's take e to the 2x and write it as e to the x, e to the x in the top here. Like that. And now this becomes the integral of minus v over 1 plus v dv. I know how to do that one. Really, I do. I'm going to add 0 on the top. This is all the tricks we did at the end of Calc 1, at the beginning of Calc 2, where we started looking at all of these stupid integral things. Like, well, what could I do? I could do partial fractions. I could do integration by parts. I could do all sorts of weird. Sometimes you add 0. Sometimes you multiply by 1.
Should you do another U sub if you want to? Or is that not possible?
Well, if I do another U sub, what am I U subbing for?
V plus or 1 plus V.
If I do that, what's the derivative of 1 plus V?
Just V.
Right, and then I'll still have that V on top that I'll have to take care of. So I can do that. But it gives me a slightly different, it takes me to the same place that I'm about to end up.
Yeah.
So we'll come back to that. We'll do it over here. I promise it does work the same. Because what happens here is I get 1 minus 1 plus V over 1 plus V. And that's 1 over 1 plus V minus 1. What's the integral of 1 over 1 plus V? Minus, which means I get ln of 1 plus e to the x minus e to the x. Now, Cody, you wanted to do a sub for 1 plus v, right?
Yeah.
So let's say y equals 1 plus v. then minus v is 1 minus y, right? So this integral, negative v over 1 plus v, becomes 1 minus y over y, which is 1 over y minus 1. Isn't that exactly where we just ended up? 1 over thing plus, aha, it gives me the same place. So yes, that works too. Lots of different ways to solve the integral. Your magical bag of tricks. Okay, now here's the fun part. That was U1. I need U2. U1 equals, crud. U2, what was U2 prime? U2 prime is W2 over W. What was W2? And then over W is going to be 1 over e to the minus 3x. Multiply to simplify here, and I get e to the x over 1 plus e to the x. Wait a minute. That means U2 is the integral of e to the x over 1 plus e to the x dx. The derivative of 1 plus e to the x is e to the x. Oh, goody. This is a direct U sub. So v equals 1 plus e to the x dv equals e to the x dx. And this becomes the integral of 1 over v dv, which is ln of v. So I get U2 is ln of 1 plus e to the x. Whew. Now, our yp. What's yp? U1 was all of this. Ln 1 plus e to the x minus e to the x times y1. What was y1? Plus u2 ln 1 plus e to the x times y2. Oop, I'm off the bottom of the screen. That doesn't help. What was yc again? Our original solution was c1 y1 plus c2 y2, right? c1 y1 plus c2 y2. Now, I, being the geek that I am, did this problem out and then went, I wonder if I'm right. And rather than look in the back of the book, I threw this in Wolfram Alpha. And Wolfram Alpha gave me something different. Not hugely different, but only one thing was missing. When I did this in Wolfram Alpha, I got y equals c1 e to the minus 2x plus c2 e to the minus x plus ln 1 plus e to the x e to the minus 2x plus ln 1 plus e to the x e to the minus x. What's missing? That piece, right? But it's really not missing. Because what happens when you multiply those together? Which means it's hiding in here. It got absorbed. So even though we did everything perfectly right, the computer gives me a different answer because it simplified where I didn't. That sucker got slurped up. Whew. Yes, ma'am. Once you've gotten to here, this line, you've done all the work. I'm really kind of happy once you give me this. I will also say that please understand that the biggest part of this is setting up. This is very mechanical. Once I have the corresponding homogeneous solutions, this is do a determinant, take an integral, do a determinant, take an integral, do a determinant, take an integral, over and over and over. This is perfect for coding. This is exactly what technology is designed for. If I am stuck having to do this by hand every time, I'd rather beat my head against the table. It'd hurt less. So how often do you think I'm going to force you to do this sort of stuff, Mia? Not very. It is possible to do this for more than a second order differential equation. If I had a higher order differential equation, then I'm going to have more pieces in my corresponding homogeneous solution, right? And that means my Wronskian is going to get bigger. I'm going to have to take n minus 1 derivatives for each of those n pieces. So if I have a third order differential equation, I'm doing a 3 by 3 determinant. A fourth order, I'm doing a 4 by 4. Bleh. Come on. You want me to do expansion by cofactor and minor on a 4 by 4 in any reasonable amount of time? Oh, I'm going to be clawing my eyes out. But I can do that. But I'm also going to get a W1, a W2, a W3, a W, all the way up to Wn. I'm going to have to take each of those columns one at a time and replace them by a column that looks like this, where there are n minus 1 zeros. And WK has B in the kth column. So I do W1, and I'd replace that first column with this thing. And I do W2, and I'd replace the second column, and W3, and so on. And then UK prime is WK over W. So after I do all the different matrices I need to do, when I take, let's see, there'll be n+1 determinants involved. Then I'm going to have to do n different integrals. No, this sucks. It works, but it's not easy. Page 164. Bottom of the page. Here. Here are the 4 matrices you need just to do a 3x3. And then for each of those, you're going to take whatever the result is here, divide it by that, and you're going to get U1 prime. You're going to divide this by this to get U2 prime, and this by this to get U3 prime. Then you're going to have to integrate each of those. And this is just to find the non-homogeneous part. Yep. It is also possible that when we do one of these integrals, we might get something that doesn't have a closed form. Something where I can't actually solve the integral in any nice term. These are the sorts of things that when you shove them into Wolfram alpha, you get something like SI of x, the Fresnel sine function, which is just a fancy way of saying, no, but we can't do the integral. So if that's the case, we could leave our answer in terms of an integral defined function. I'm going to try and avoid those sorts of problems because they don't really show me anything useful. Except, okay, now when I actually want to find a number here, I got to do a numerical approximation, which means I either have to use a trapezoid sum or a Simpson's rule or something to figure out the value of the integral I need to go from 0 to whatever. It's not worth it. I'll save those for the numerical methods class. This is my pitch. You should take that next semester. Questions? Yes.
So we need to know how to multiply like a 3x3 matrix.
How to do a 3x3 determinant?
Yeah.
I would hope you do. Did you take linear already?
No.
Oh, okay. So you're the exception then. That's right. I think everybody else in here has had linear. Okay. Let me give you the quick and dirty version of this. A 3x3 matrix, to find a 3x3 determinant, you're really doing a sequence of 3 2x2s. I just made this up, so I have no idea what the answer is. But if I want to do this determinant, I want you to pick a row or a column. Doesn't matter which row, doesn't matter which column. I'm going to make my life easy. I'm going to go down the first column. Now, in my head, I'm making a little checkerboard. When we did the 2x2s, we added and then subtracted. Right? Well, these are the signs I'm going to use for this one. So I start with this, going down this column. So I'm going to take that 1, I'm going to put a plus in front of it because there's a plus here. And then I'm going to chop off the first row in the first column. What's left in my matrix if I chop those off? A 2x2. Now I go down to the next number. I put a 3, that gets a minus sign. Chop off that row and that column and write down the remaining 4 numbers. Then I do it for the bottom and I write a 0 and I put a plus in front of it. And I chop off the first column in the bottom row. 2, 7, 4 minus 5 is what's left. And now really I know how to do the 2x2s, so I'm good. Every larger one chops off one row, one column, and then you get a smaller one each time. This is the expansion by cofactors and minors that I just mentioned. I went down the first column. You could go across the first row. You could go across the second row or down the third column. It's up to you as long as you follow this plus and minus pen. To me, that actually gives me a hint, especially when I look at the 3x3s at the bottom of page 164 again. Notice that in W1, W2, and W3, there's a column where most of it is zeros.
Yeah.
That's the one I'm going to go down because that's going to make my life easier. So with a little bit of construction, let's see, we get 1 times 24 minus -5 minus 3 times 12 minus 7 plus 0 times whatever, I don't care because it's times 0. So this is 29 minus 3 times 12 minus 7 is 5. 29 minus 15 is 14. The problem with the ones we would be doing for this course is they would not just have numbers in them. They'd have functions.
Like Gaussian and the one like +4 and 1, 7 and 0, 6. Because you take out the row.
So say that again.
I chose like to do 4, the middle one. And it would be 4 and then make it be 1, 7, 0, 6.
Yes, because I take out the middle row and the middle column. Yes. Whatever number you're on, that's the row and column you cross out.
Okay.
Wrong button. This button. I am going to tell you, though, that because I'm the kind of guy who really doesn't like doing a lot of this stuff by hand over and over and over and over, one of the websites I listed, in addition to Wolfram Alpha, way down there at the bottom, says math24.pro differential equations solver. People, check your work. I'm begging you. And you can tell it what method to use. And it will not just give you an answer, it will walk you through a solution. And on all the ones I did, it got it right when I checked stuff in there. I can't say that about a lot of programs, but this one I could. So I recommend this one heartily. Questions? Yes.
I was looking at the homework and 4.6 instead of that was instead of late, sorry.
36 has a question mark on it, right? It's a bonus problem. This is today. Oop, doesn't help if you can't see the page. There. This is today. That's the end of next week. Tomorrow's question and answer. Then I got 2 more sections. And then another question and answer. And then the homework gets turned in. Then we have an exam. Okay? The review sheet is posted. Now, I will point out to you, in addition, this Laplace transform discussion is one of my favorite things that we're going to do after the next exam. And I happened to get really lucky. And last week, 3 Blue, 1 Brown released a couple of videos. The first one was on why complex variables make things go around. And the second one was on what's a Laplace transform anyway. So I'm going to give you a series of 3 videos to watch after the exam or during this question and answer day sort of deal. Because we're going to get here and you're going to be like, what the f is going on? His videos are amazing, getting under the hood. Not just I'll give you the definition. The definition is easy. It's like learning what this is and then learning how it works. They're two different things. I can drive a car. I sure as hell can't build an internal combustion engine. I can do the integrals involved in a Laplace transform. Understanding why they're the things we want to do is a whole nother question.
I just tried. Putting up, the whole page over and says the web page is blocked.
Oh. What? The hell do you mean this thing is blocked? When did you? Okay, so that's a certification in invalid spot on their end. I'll figure out why it's going on. It may very well be blocked from the university then. So yeah, we'll try it at home. I don't know. It worked from my house. All right. I will see you all tomorrow. Have a wonderful rest of your day.